Hello, I'm Sue Nelson, and thanks for joining me on Create the Future, a podcast brought to you by the Queen Elizabeth Prize for Engineering. Many engineering designs begin on paper, and in Mark Schenk's case, he's taken that expression quite literally. He's a lecturer in aerospace engineering at the University of Bristol, and one of his research interests covers origami, the Japanese art of paper folding. How did you get into origami?
My mother did origami when we were children, so I was always aware of origami as a plaything, as a pastime. I never pursued it very much, but it was more when I then got into my PhD phase when origami became an option for a research topic. I knew the concept, and then it made sense to start continuing that, basically.
I can't help noticing that there's a box here with some paper designs in it. Just bring it out for me.
Right. Bring So these are kind of demonstration models I use during public lectures to demonstrate the various features of how you could use origami for engineering, basically.
Now, this one is lovely. It's bright red. It's not, when I think of origami, I think of some little bird or, a little frog or something, whereas this is like a concertina that we can push it in and then pull it out and expands in a sort of zigzag fashion.
Yes, I think engineering origami is much more geometric than, for example, the bird or the crane you're probably used to. So one of the main reasons is you kind of tend to repeat a pattern. So in engineering, it's easy to take one simple pattern and repeat it over and over again. So in this particular pattern, you take one kind of fold, which you move in two directions to make a large sheet. And that gives you it makes it easier to design analyse, basically.
Let's have a look at some of the other ones in here as well. Are these exactly the same shapes? Because they look them to me, again, it looks like a zigzag.
They are the same shape, but then formed into a tube. So the previous one was a kind of a flat sheet, so it's a flat sheet of paper that folds up into a 3D shape. This one is a tube of origami, basically. And that's the same pattern again. This is the most common pattern you will find. So this is named after a Japanese physicist called Miura. And this is the fold that most engineers tend to use for their applications.
And what applications would that have, that folding side of zigzags? And in fact, I've just noticed you've got a wonderful one here in metal. It's absolutely gorgeous.
Yes, it's gorgeous once you've made it. Making it took quite a lot of effort. So this is, again, the same pattern, but this is made from stainless steel. So again, this is folded from a single sheet of stainless steel. And it looks, it's very nice. But it does become less foldable. So because it's made from steel, you can't easily fold. So the paper ones are very easy to expand and contract, whereas the metal ones tend to be more of a fixed shape.
And then there's this shape here in your box that is not like the others in that it looks more like a flower, a two-dimensional flower, which you've now just pulled out. So it looks more like a sort of something that would go into the flexible tube that would go into your washing machine or something. But is it foil?
It is. It's actually the exact same pattern as before. So I said this is the most common pattern I said before. This one is just, rather being flat, is now in a circle. So this is made from a foil. So this is 3-layered. It's a very thin material. The material is about twice the thickness of a human hair in total, but it's aluminium, then mylar, which is kind of like PET, so like shopping bag material, and then aluminium again. And this is a prototype for an inflatable, deployable structure we launched in orbit a couple of years ago. So this is the prototype of that. So what it is, it's a origami cylinder. So when it folds up, it's a really compact shape. You then inflate it once in space, and then it deploys from something which is about 6 centimetres tall to about 1 metre in length, and it forms a very smooth cylinder. So we launched this a couple of years ago on a small CubeSat satellite, which is like a really small satellite the size of the best description I've heard for a CubeSat is the size of a whiskey box. Basically, it's 10 by 10 by about 30 centimetres, but that's about the size of a good bottle of whiskey. And we launched this inflatable boom, origami boom, on this satellite. So it was launched in orbit, then inflated and deployed to full length.
That's great to think that that's this tiny, small prototype then has an application on a spacecraft. But then when you see it like this, you can totally get that, because weight's important, volume is important on a spacecraft. So you then have something that is very lightweight, but also once folded up, which is where the origami comes in, takes up hardly any space at all.
Yes, and that's one of the motivating reasons for exploring origami in engineering. Classically, you start with a flat piece of paper, you make it into 3D. But the other way around, if you need something which is 3D, you want to fold it up small. Origami is a technique for doing that. So this particular case, when I started on this project, this was a project back at the University of Surrey when I was there. I was thinking of how to design one of these inflatable booms, and origami was kind of the last thing on my list because it was really hard. It's quite hard to make. That's the downside. But this turned out to be an application where, given what we wanted to achieve, origami became the only real option for this particular application. So I tried my best to avoid using origami for this particular mission, but it ended up being an origami pattern.
And what other structures, I can think of one for starters, are in a spacecraft that will benefit from this folding one, the most obvious being solar arrays?
Yes. Well, again, I think what I could have hinted at before, making them in an origami pattern can be quite challenging. So quite a few solar arrays are designed to fold up because there's only so much space in a rocket fairing. And when you get to orbit, you want to unfold them because you want a large surface area to get more power. And origami has been proposed for this. And actually, the Miura pattern I pointed, the one we had before, had actually flown in orbit in 1995. JAXA, the Japanese Space Agency, launched this particular pattern.
How appropriate.
Yes. It was actually designed by Professor Miura, whose name is attached to this pattern. He designed that. But it's always been a prototype. So most panels you see, if you look at the ISS, for example, the International Space Station, the solar arrays there are much simpler. They are literally a concertina fold. So just back, forth, back, forth, back, forth. Whereas these are a bit too complicated to launch in orbit. But yeah, that's the obvious application for origami is solar arrays. But also solar sails. This is where you don't use sunlight for power, but for propulsion. So where literally the photons hitting your spacecraft push your spacecraft along. So it needs to be very large and very light because there's not much force coming from sunlight. Again, the Japanese Space Agency has explored using origami patterns for these kind of solar sails. So that has also been launched in orbit, kind of origami patterns for solar sails. And it makes more sense there because these are very large, very thin membranes that have to be kind of unfolded once in orbit.
And where do you see this extending further, perhaps into the future, with other parts of a spacecraft? I mean, you mentioned boom, and booms could be antenna as well. Booms are often used with the instruments on hanging from them. Are there other applications that could benefit from this?
So people have looked at kind of antennas for small satellites. Again, these things tend to be designed for very small satellites. For larger satellites, there's less of a push for compacting it as much. So people have looked at origami patterns for small antennas for CubeSats, reflectors, so having a large kind of surface area to receive a signal from the ground. Solar arrays again, but again, these tend to be quite simple fold patterns. So the ones you see in front of you are quite intricate. They tend to be a bit simpler once you launch them. But those are kind of the main applications: antennas, reflectors, booms, and sails.
It's lovely the way a childhood interest has sort of ended up as part of your sort of professional life. So we know that you were interested in origami as a child, and obviously it came in useful later. When did the interest in engineering start? Actually,
quite late in a way, because I'm one of those classic students who was very good at A-level in maths and physics. And if you're good at maths and physics, one of the options is engineering. So for me, it wasn't a really conscious choice at the time, whereas now looking back, I'm an engineer through and through. I couldn't have picked better, but at the time I picked it because it was the best fit to my skills. It's only once I was actually in the field and discovering what engineering actually is that I became a real engineer. So we get a lot of students coming to aerospace engineering who are really fascinated by space or aircraft, and that's one route into engineering. But for me, I was good at problem solving, I was good at math and physics, and that got me into engineering. So there's no deep inspiration there other than once you start in engineering, you'll probably learn to love it.
And it was a good fit. It was.
Yeah, absolutely. I couldn't have picked better. But you don't know that until you look back and go, yeah, this was exactly what I needed.
You sound British, but there's just a touch of an accent there because you're from the Netherlands.
Yes.
It's funny you like foldable, compact structures when you're from a flat, sort of fairly compact country. I don't know whether there's any psychological interest there.
Not I can think of, I'm afraid, no.
So where did you study? What did you study?
So I did my degrees in Delft, which is one of the three big engineering universities in the Netherlands. So I did my degree in mechanical engineering there. And in my master's, I picked biomedical engineering, still within mechanical engineering, but it was more biomedically focused. And after, so that was about 6 years in Delft. And then I moved to Cambridge for my PhD. And then I moved from mechanical into more civil structural, where these deployable structures, these origami structures, were part of that research group. They've been looking at deployable structures in the past, and at the time it wasn't kind of a logical next step was to further explore origami as a deployable structure. That was kind of the motivation at the time.
I was at Delft, actually, the technical university there last year, looking at their research on robotic flying insects, which were really interesting. And you mentioned this biomedical specialism. Did the origami have any application with biomedicine there, or was it something totally different that you were working on?
Completely different. But it was actually, but linking back to just what you said about the flight robotics. So one really interesting area where origami is being used to understand how nature works is actually for flying insects, where you can imagine having a ladybird, for example. They've got these hard scales under which they fold up their wings. So the scales kind of pop up, the wings fold up and fit underneath the scales. And that folding pattern is actually something that's currently being studied, so using origami techniques. And it's not that really designing it, but it's more understanding how they fold it up. So it's a bit of a diversion, but
it's an interesting one. Yeah.
Linking back to the flying robotics, origami is actually being used in that area to understand how insects like ladybirds, like earwigs, fold up their wings. But no, so there was no direct link for me personally between the biomedical side of things and origami. There are links nowadays, but there's quite a lot of work happening in applications of origami which have biomedical links. So, for example, people have looked at using origami for stents. So these are little deployable structures that you place inside somebody's artery to kind of expand it to get the blood flowing again. So some people in Oxford have explored that. People are using origami for small kind of robots that you can ingest that can actually crawl through your digestive system. So there's quite a few applications being explored for origami in biomedical, but for me it was, in that sense, a bit of a fluke that I ended up doing origami afterwards. There was no direct link for me, at least.
Now, we're in your office at the University of Bristol in the engineering department in something called the Bristol Composites Institute. So what goes on at this institute here?
So this is kind of a large group of researchers all working on composite materials. So the classic example is carbon fibre composites. So most people would associate that with racing cars, but also modern aircraft are largely made from composite materials. So, for example, the Airbus A350 is at least 50% weight is composite materials. And so these are basically, you make a material by having these fibres, very, very small, thin fibres. So these are a fraction of the thickness of a human hair, but you put thousands of them side by side in very thin layers. And you can build a material by kind of putting these layers at different angles on top of each other. And the reason we like them is because they are very light, or they're very stiff and strong for how light they are. So they're comparatively very, very, very stiff and strong. So for the aerospace industry, it's interesting for weight saving primarily. So a lot of the work happening in our group is around making lighter structures. How do you manufacture using composites? But quite a few people, including myself, also use composites for shape adaptive structures. So using composites to make structures which can change their shape very easily. And this is where the fibres come in, because you can, let's say, if you have a sheet of aluminium, for example, the stiffness, so how hard it is to kind of stretch the material is the same in any direction, basically. If you make a composite, you can make it more stiff in one direction, more or less stiff in the other way, and you can really tune how you can use the material. So we make these shape-changing structures using these kind of composite materials.
And is this why I noticed on your research page it said zero stiffness structures? So does that relate to something that is not so stiff in one direction, as you said, but is a bit more flexible in the other?
Yes, it's a very niche research area, but yes, it is exactly that. It's making structures which have no stiffness in certain directions. These don't relate strictly to composites, but they are types of structures which are used, for example, in compliant mechanisms, which is so in the classic mechanism. What you want is it's a mechanism where you've got hinges and links and springs, and what people try to do is make mechanisms where you don't have hinges, you don't have springs and all that. And what you want to make it out of a single piece of material. So rather than something rotating like a hinge, you have something bending. The advantage is there's no friction because there's no joints moving past each other. The downside is that there's stiffness. You want to move it and there's a stiffness. Now you can design certain structures to then compensate for that stiffness. So if you make something which has a positive stiffness, something which has a negative stiffness, you add them up, you get zero stiffness, and it allows you to make something which can deform shape very easily in some direction. So we don't use composites for that much yet, but it is the same idea, using materials to design stiffness where you want it to be.
And do they have applications other than the aerospace industry?
Composites or zero stiffness?
Zero, but both.
both. Well, the classic example of a zero stiffness structure is pretty much on every UK's desk. The classic Anglepoise lamp is a zero.
And there's one behind you.
There's one behind me. Yes. Well, I bought that one to show in my lectures, basically. So the first years get the benefit of me talking about a lamp for 15 minutes. And they do wonder why I find it so exciting. But then I explain why it's so interesting. Because the idea behind the lamp, behind the Anglepoise lamp, is that you can reposition it in any position you want. So changing it from one position to another requires no force, so there's no stiffness. And that's done by having these springs. If you look at all these lamps, there's like these springs at the bottom, and by moving your lamp around, the springs extend and contract. And as a result of that, you feel no stiffness. So that's a very classic application. Other applications are mechanism design, so where you have a compliant mechanism where you don't want that stiffness, so you can remove it. Those are the main applications for zero stiffness. Composites are much wider. You'll find composites pretty much everywhere around you. Space being one of them as well.
And in terms of structures that have this lovely mix of origami and engineering, we've talked about them so far, particularly with use to a spacecraft. Yeah. Where else could this be applied?
You can't go to a shop and buy many origami products just yet. It's not very common in industry yet either. We're exploring it for quite a range of applications. Deployable structures is one. So, for example, tents or deployable shelters. People have explored origami for that. But also in more unexpected places like robotics. People like the idea of using origami for robotic actuation. Again, the same idea that you can fold something up, make it small, and deploy it. You can also imagine a robot arm which is based around an origami structure. And this kind of fits in the field of soft robotics, where the picture most people have when they see industrial robots are these big, huge, chunky robots. If you picture like a factory that makes cars, you have these big, chunky robots. They move around, they pick up huge parts. They're really, really stiff. So if they hit a person, for example, this is quite dangerous. Whereas if you make robots which are much more flexible, if that robot then hits a person, the robot will just deform. So it's a kind of a field where soft robotics is kind of being explored for human interaction, so robots that can interact with humans, and origami has been explored within that as robotic arms, for example. Yeah, that's kind of an area where it's being explored.
It sounds like it's been incredibly useful to look at things slightly differently. Mm-hmm. I mean, I know, engineers are always described as problem solvers, and that's true. But whenever something new or different has come along, it's when somebody has looked at something and forgotten what the existing way of doing something is back. So take Dyson and his vacuum cleaners, the shape and style which we're all used to now. Mm-hmm. just wasn't in existence at that time. They all looked exactly the same, and they were always designed in a same way. Is that because of using origami, you get to look at things, taking things that are almost feel like two-dimensional structures, like a piece of material or a piece of metal, or whether it's just cardboard or paper, and then folding it in a way to give yourself a totally different 3D design. It's something, I know that computers do it all the time with CAD, but it's a lovely way of viewing things, isn't it?
I'm not sure I can describe it better than you just did. It does open up. So you have to think in a certain way, and also also origami requires quite a few fields to come together. So there's a lot of mathematics involved, so quite pure mathematics. There's mechanism theory, structures, design. You need to be aware of quite a few things to be able to combine quite a few fields to be able to study origami, because they aren't really like a structure, they aren't quite like a mechanism, there's somewhere in between, so you need a quite breadth. So I think that links back a little bit. It does bring together quite a few different fields, which is always good for getting inspiration from different areas.
And what about your teaching? Do you obviously you've got one prop there with the Anglepoise lamp.
Yeah.
do you get the origami out for your students?
Yeah, pretty much every year I teach, I show origami as an example, yes. So the first years, for example, when I talk about deployable structures, so I teach mechanics to the first years. So basically Newton's laws, if I apply a force, what's the acceleration? And one of the examples at some point is a deployable structure. So I will talk for quite a while during the lecture about the origami projects I've worked on in the later years as well. They keep coming back as examples. I think by the third year they've seen my inflatable origami broom quite a few times by that point, but it gives a bit of a red thread, as in there's so many interesting things around that example that keeps coming back over the years. I'm currently teaching a fourth year unit where I managed to squeeze in origami as well as an example, and it fit perfectly, but nobody else would have put it in except somebody who works in the field. Yeah.
And so what are you researching yourself on in between? When you're not teaching, what's the project that is really firing you up right now?
Well, there's always the origami work is continuing. So I've got a PhD student working on that. So that's always in the background, continuing. Other things we're working on at the moment is kind of linking to these shape-changing structures I talked about before. So having a structure that can rapidly change shape. So the example we tend to use a lot, it's not my work so much as my colleagues' work, is an air inlet which can change shape automatically as for different air speeds it would open and close. And it's based on the same idea as when you take a ruler. If you take a ruler, you compress it. At some point, it will suddenly snap sideways, and that's called buckling. And you can use that effect. So normally you see it as failure. If it buckles, it's probably failed. So we design buildings, for example, to avoid that. But you can also exploit it, because you can imagine that you get a really rapid change in shape. So people use that for that kind of idea for example, an air inlet which can open and close automatically as the air speed changes. But what we've discovered is we're pretty good at calculating them, prototyping them, but the testing is actually really quite hard. So we're developing new techniques at the moment. It's kind of my main kind of topic at the moment is developing techniques to properly test them, because we know that they work, we can calculate it, we can show it. It's just if you want the industry to start using them, you have to really validate them properly. So we're looking at techniques that kind of can test these buckling structures. So that's the main topic area at the moment. So moving away from origami, but shape-changing structures still there.
And how do you feel at the moment in terms of the number of people wanting to study engineering? I know Bristol is an incredibly popular choice.
We're heavily oversubscribed. So yeah, that's good. There's a lot of people wanting to study engineering, and in a way that's because the main skill an engineer learns is problem solving, and whether you apply it to aerospace engineering, mechanical engineering, or even banking or finance, it's that mindset that really is your skill basically. So the fact that a lot of students, that's a good thing. The capacity is another problem. There's only so much capacity we have to teach students, so we are very oversubscribed because a lot of students do want to do engineering, which is good.
What would you say to anybody listening who wants to study engineering? What would be your sell, your pitch to, whether it's because of how it's affected your life or the enjoyment, what would you say is the big thing that why study engineering?
Oh, that's a tough one. I think it is problem solving. It's the ability to solve problems which have not been solved before. So there's plenty of problems that need to be solved, making aircraft lighter, more fuel efficient, to wind turbines, to new renewable energy sources. So all of those problems which we need to tackle, we need engineers for, because we need problem solvers. That's the main motivation. You can actually change the future in that sense.
That's brilliant. And I just want to know whether, do you ever do origami for pleasure now and actually do make cranes or frogs or thing, or is it now totally part of this is work?
Unfortunately, it's become entirely work. I was never very good at origami folding, hence the simple patterns. But no, it is for me, it's work. But that said, if you look at some of the biggest names in origami engineering, they tend to be artists as well as mathematicians and engineers. They really like both sides. For me, it's my job, and I really, really enjoy it. But I don't come home and fold a crane.
Great. Mark Schenk, thank you very much for unfolding, sorry about the pun there, your engineering career with me on the Create the Future podcast.
My pleasure.